Welcome back to this project. So in the last video we loaded, normalized, and pre-processed our data set, and thank you for doing that along with me. We are now ready to dive into the all-CNN. And so in the Striving for Simplicity paper, they defined these model architectures for us. They tested a couple A, B, and C. This model C is actually the one that they end up using, and it's also going to be the one that works the best. So this is the one that we're going to use. If you have the time and you want to understand more about this network, I highly recommend reading through this paper. They dive into some really cool things. They also talk about data augmentation, which we will mention briefly later as well. But for now, let's just go ahead. I'm going to copy this model architecture out of this paper and into my Jupyter Notebook so that we can reference it easily. And so we'll also start by talking a little bit about markdown cells. So instead of a code cell here, I want a markdown cell. This again is just denoting that it's going to be text. Right now we're going to have to process this a little bit though, so it's in a usable format for us. For these layers, we see that out of the table it copied the first ones as well. We only want the third one, so let's delete those first couple guys so that we only have that model C. Okay, here we go. So there's the model C. Let's go ahead and make these bullet points. So each layer is going to be a bullet point. You can do that just using an asterisk in the markdown. So I'm going to go through these really quick, and we'll get bullet points here. So as you can see, this is all convolutional layers. We have a couple max pooling layers, and then a global averaging, as well as a 10-way softmax is actually what we're going to use. So here we go. And let's say we'll call this, because that's its name, the all-CNN C network, used for classification on CIFAR 10. Alright, so if we do Shift Enter here, we now see we have this nicely defined model C. Each layer here is a bullet point, so we can reference this. Instead of clicking back and forth to this paper, we can just look at it in our Jupyter Notebook now. Okay, so let's start by importing necessary layers. So we're going to take these right from Keras. So we can do from Keras.models import sequential. We're going to have a sequential model here. That just means that we're going to add the layers one after another. From Keras.layers, we're going to import a dropout layer, which we're going to use for regularization. Dropout is a common way to prevent overfitting of networks. That's common with neural networks. We'll talk about that a little bit more later. Activation, so we can have a couple activation functions. Conv2D, this is the convolutional layer, the main convolutional layer. And then we're also going to have global average pooling 2D as well. From Keras.optimizers, we'll import the SGD. This is the stochastic gradient descent. That's how it's going to optimize this layer. Okay, so let's run this. Those all import correctly, so we're good to go. So we're going to wrap all of this in a function. So we're going to define that here. So we're going to define this as a Python function, the all-CNN. And so we can start adding in our layer types here. So although we're going to actually have to start by defining the model type, which is of course going to be sequential. So to do that, we can just say model equals sequential. So we have a sequential model. And now we can go ahead and add model layers. Okay, so to start, we have an input. We don't have to define our input, but we're going to have to tell this first convolutional layer that it needs to accept an input. So let's start by just model.add And Keras makes it this easy. Once you have started a model type, you can add layers by simply typing this .add and then the model type, or the layer type. So we have conv2d, that's our first layer. We want a 3x3 convolutional layer. So this is going to be with a 96 parameters, a rectified linear unit activation layer. So we're going to have 96, comma, we want this 3x3. Let's do a space here. Padding we're going to have to define. We can just say this is same. And then we got to tell it to accept an input. So input shape is going to be 3, 32, and 32. Because remember up above, when we had our images, these actually had the channels listed first. So they're 3 by 32 by 32. That's our input shape. And that's what we need to pass to this first convolutional layer. Okay, so there's that. What we can do now is we can add this. It needs to have a rectified linear unit activation layer. So we can do model.add activation. And this is just going to be the rectified linear unit. Probably the most common activation function in convolutional neural networks today. Okay, and we can keep going. So model.add, another conv2d, 96. Again, this one is 3x3. And same as before, padding is going to be equal same. We don't have to define input shapes anymore, so that's good. But we do need to add an activation layer to this. Activation, rectified linear unit, there's that. All right, we're up to this max pooling stride 2. So this is, again, just a convolutional layer, but we're going to have to define a stride. Oh, and I would have had an error here if we have fixed that. But again, 96, 3, 3. Padding equals same. Strides, though, we're going to define here as 2 by 2. So there's that. And actually, after this layer, we're going to add a dropout layer. Model.add dropout 0.5. So dropout layers randomly will pick out specific neurons and prevent the network from using them. So it's going to drop neurons randomly. And this helps the network generalize. So instead of having individual neurons that are controlling specific classes or features, the features are spread out over the entire network. And this is going to produce a network that is better at generalizing. It's going to be able to handle new data better. It's going to prevent overfitting on the training data set, so it's going to perform better on the testing data set. Dropout layers are really important. But again, in this project, I'm not going to dive into too much detail in these specific layers. If we went into the math and the theory behind all of these, and we dove into that, we would all walk out on the other side with PhDs, and we don't have time for that. We just want to look at how we use and deploy these models. So we are not going to go into too much of the theory, although I will mention it briefly like I just did for the dropout layer there. All right, so let's keep going though. Model.add, we're going to have some more convolutional layers here. So conv2d, these though, they get a little bit larger. So 192 neurons here, still 3 by 3. Padding equals same, good there. Model.add, same activation, rectified linear unit. Model.add, go back up, so we're right here, another convolutional layer. Conv2d, 192, 3 by 3. Padding equals same. Once again, model.add, an activation. Each convolutional layer is going to need an activation function, so we'll add that there. And model.add, this is going to be our max pooling stride 2 layer again. So conv2d, and this is going to be the 192, 3 by 3, padding equals same. And just like we defined it before, strides is going to be equal to 2 by 2. Okay, just like in the previous section as well, let's add a dropout layer. Improve our generalization here. So there's that. And now we're into our last section. We've got these guys here. So we have a 3 by 3 convolutional layer with 192 parameters, and it drops down to a 1 by 1, and then finally a 1 by 1 with 10. Our number of outputs here is 10, so that's why we drop down to that 10 there. So let's go ahead and add these. So we'll do model.add conv2d. We start with the 192. However, it has the 3 by 3 still. Padding equals same. There's that. And again, this needs an activation. So we'll add that on there here. Rectified linear unit. There we go. All right, now we get to switch things up a little bit. So we have a conv2d. Still has 192 neurons. However, this is going to be a 1 by 1. Padding, and we're actually going to switch this a little bit as well. Padding equals valid. Although this still needs an activation function, so let's add that on here. Rectified linear unit. There we go. Finally, model.add. Condense this down into our 10 outputs, 1 by 1. Padding equals valid. All right, there we go. So we've gotten through the convolutional layers. Now we have this global averaging over 6 by 6 spatial dimensions. We can simply use we'll add a comment. Add global average pooling layer with softmax. All right, so to do that, we'll have model.add global average pooling 2D. We need a couple parentheses there. We'll also do model.add activation, and this is going to be a softmax activation layer here. Okay, so here's all our layers. We followed the model structure or architecture that was defined in the Striving for Simplicity paper, and we have implemented that now in Keras. So we got to add a couple things to the end here. We want to load the weights option here. So this is how you would load pre-trained weights in Keras. You simply type model.load weights. And what I'm going to do is I'm going to add up above here is we're going to be able to pass weights to this function. So weights, though, the default will be none. So the default will be activating from random weights. However, we'll be able to pass pre-trained weights to this function if we so decide to. And then finally, at the end of this function, we've built all these models, but we need to return it. So we'll do return model. So now when we call this function, the all CNN functions, it will define this model, a sequential model, add all the layers to it that we just defined up above here, add a global average pooling layer, load the weights if we pass them to them, and return that model to us. All right, so we're good to go here. Now we get to move on to defining the parameters and actually going and trying to train this model. So let's go ahead and click Shift Enter here. This will just build this function. It won't actually do anything for us yet. So let's go on. So let's define some hyperparameters. These are just generic convolutional neural network training parameters. So we're going to have like learning rate, how quickly we should update our weights. We'll have a weight decay. Try to prevent improve our generalization again. Momentum equals 0.9. All right, so here's some hyperparameters. You could play around with some of these if you wanted. These are pretty generic. And again, I'm not going to dive into the theory too much just because we would be here all day. In some of our other projects, we've looked at how you would do a parameter grid search to find the optimal parameters for a neural network. So if you wanted to kind of do that for this as well, you could do a grid search and build that as well. All right, so now we're going to build the model. So model, we can simply call that allCNN function that we defined above. So this is now going to return the model, which will be defined here as the model. So that's perfect. But we're not quite there. We need to define an optimizer and compile this model, actually. So our optimizer is going to be the stochastic gradient descent. So we'll call the class SGD, which we imported above. And now we need to pass it the hyperparameters that we just defined. So for example, learning rate gets passed as just LR. Decay is going to be our weight decay. Momentum, simply equal to momentum. Define that above. And then we need this last parameter, actually. So we'll add that in there as well. And then model.compile. So this is going to actually compile this model for us. If I can type here. With the type of loss that we define. So for this, we want a categorical cross entropy. So this is a multi-class problem. We have different categories. We're going to use our optimizer, which we defined as the SGD above. And then metrics, what we want, a good one, a common one, accuracy. So how accurate is our network? That's what we want to be optimizing and outputting as our metric. Okay, so we can see the model. Let's go ahead and print the model summary. So to do that, we can simply type print, and then we'll do model.summary. So print that out. So this will tell us what our network looks like, the architecture, make sure we got all that correct, the number of parameters, stuff like that. So let's actually go ahead and do that here, and so we can see if this is all running correctly. So this is going to build and compile this model, and then print out this summary. So if we've defined everything correctly in our function above, everything should work. All these layers should work correctly. But let's just check that by running this cell here. So this is going to think for a little bit. And so we did have an error. Global name weight is not defined. So weight, if weight, it's because we needed a plural here. So we did have an error. So let's go ahead and fix that. I'll run this one more time and see if we get better results. And so here, we're going to have to change this a little bit. So again, spelling errors, going to be the death of me. We need an optimizer here. All right, here we go. Just fixing out all these bugs. A lot of programming is getting errors and going back. And here we go. We actually worked this time. So we have all these different layers, which we defined above. This just tells you a summary of each, the activation layer for each. And it gives a name to each layer, the output shape, the number of parameters. So total number of parameters we have is 1.3 million parameters here approximately. All of those are trainable. So updating 1.3 parameters, that's a serious computational task, but that's okay. I'm just going to add on right onto this cell. Let's start defining additional training parameters and actually fit the model to our training data. So define additional training parameters. Epochs, we'll do 350 epochs. This is actually based off what they do in the paper. They define some of their training procedures in here, as well as a batch size of 32 images. So batch size simply means you're going to run 32 images, and then after those 32 images, you can update the loss or update the parameters instead of updating them individually after every single image. All right, so there's some additional training parameters. Now if we fit the model, we'll do model.fit xtrain ytrain. Validation data we have to pass as well, but that's okay. We already have these defined nicely. X test and the Y test, which is a one hot vector of length 10. We have epochs. We're going to pass the epochs that we just defined. Batch size equals batch size. And then verbose is going to be equal to 1, so we can actually see what this is printing out. All right. If you change this verbose to 0, it will suppress some of the print outputs. Here we go. We have this print model summary, which we had above. It's going to keep thinking for a little bit. If you actually go into the documentation for model.fit and Keras, you can see kind of what these verboses do. I think verbose 0, verbose 1, and verbose 2 are all possible parameters. Okay, and here we go. We've started training. Epoch 1 out of 350. We're updating these parameters, going through the batches 32 images at a time, training, updating the loss, and this is actually really depressing. So here we go. Estimated time remaining 1.5 hours for Epoch 1 out of 350. So this is actually going to take almost 500 hours to go through and train all of this through all of these 350 epochs. Yeah, we have 1.3 million parameters. We're updating those after each batch. This isn't that surprising that it's going to take that long. So hold on a minute. Let's dive into a brief discussion on CPUs versus GPUs and why they are so important in deep learning tasks. So I'm going to come down here, and again, I'm going to copy in some pre-made notes. So I'm going to do a markdown cell, and we'll talk about this really quick. So right now, I'm running Keras through a central processing unit, a CPU. In my laptop, I don't have what's called an NVIDIA GPU or another GPU that can handle these deep learning processes. So you have CPU, often called the brains of the PC. This is what most generic computations are run through. It's what Keras and Theano is utilizing automatically. However, some computers and laptops are actually equipped with a graphics processing unit. So originally made for gamers, these are great at handling large matrices of numbers, so consequently they're really good at deep learning. So they have been used increasingly commonly to speed up the training of deep neural networks. And honestly, it's not realistic to do these tasks on CPUs. So the most common GPUs for deep learning are produced by NVIDIA, and kind of more importantly, NVIDIA makes the CUDA drivers and CUDA toolkit, which allows you to utilize these GPUs with Theano and Keras or other deep learning packages such as Caffe or TensorFlow as well. So go ahead, if you have a GPU on your computer, specifically an NVIDIA GPU, you can download and install these CUDA drivers and toolkit and then rerun this training using that GPU. And the speed up is substantial. The original paper, The Striving for Simplicity, mentions that it took them approximately 10 hours to train this on a modern GPU. So instead of 500 hours, it took them 10 hours. So that's a speed up of a couple orders of magnitude. It's not a small difference by any means, and it makes this a more realistic problem to solve. So I'm going to go ahead, and if you see we're only on the 2,000th image out of 50,000, I'm just going to take this. I'm going to click a nice stop right here. I'm going to interrupt the kernel. I'm going to tell it, hey, no reason to be running for the next 500 hours. Let's go ahead and stop that for now. So again, if you do have a GPU on your computer, please install those different toolkits and dive into training on a GPU. However, if you're like me and you only have a CPU on your computer at this time, that's fine. We're going to look at how we can load in pre-trained weights that have already gone through this process and then leverage the network in that way. So let's go ahead and move on. All right, so I'm going to go up here. I'm going to take this cell. I'm going to do a Control A, a Control C to copy all of this, and I'm going to bring this down, and we're going to switch some things around down here.